Hey, I hope you're doing fine, because today we're going to start something great. It's called physics. And this guy over here, he's going to help me. He's a Linux penguin. Linux power. Okay, and if you're wondering who is Feynman, well, he was a great physics teacher and a Nobel Prize winner in physics. So, quite somebody. Hey, and what about me? Well, my name is Luis, and I'm gonna help you along this journey. Welcome to physics. So, what is physics? Let's start there. Well, the word physics comes from this word physis or physis, depends where you're looking at. And it's a Greek word, and it means nature. But physics is the study of nature. Okay, so that's why we call it physics from física, which is a Latin word. And in Spanish, we call it física, but with an F. Okay. And notice that it says late 15th century. So a little bit before Newton, physics was already around as a subject. Okay, so the study of nature. What exactly are we talking about when we say nature? Well, I would say it's reality, because we are part of nature too. It's not just the trees, the animals, or other things in our world. It is also us, because we are a part of this universe. Everything in the universe is nature. And it is pretty big. So if you notice in the image, it says 1 billion light years on one side. 1 billion light years, what does that even mean? Well, it's a huge number. If you recall, 1 billion, so that is a 1, and then you have 9 zeros after it. So 9 zeros, you multiply 10 9 times, and that is 1 light year. And 1 light year is actually a pretty long distance. So, but how much is it? Well, it's also pretty hard to imagine in your head. But let's try to use these, what I would say, relations. So light takes like a little bit more than a second to reach the moon. And it takes 4 years to reach Alpha Centauri. Alpha Centauri is the nearest solar system, and it takes light 4 years to get there. Okay, what does it mean that it takes 4 years to get there? Well, it means that our radio waves that we've sent out into space take 4 years to get there. Now, it takes less than a second for it to go around the Earth, but it takes 4 years to reach Alpha Centauri. It is pretty far away. If we would want to reach there with our rockets, it would take hundreds, thousands of years. Voyager is going to take a couple of thousands of years to get there. But Voyager is headed, and hopefully we will pass Voyager whenever we head over there, sometime in the future. And it's not as far as you might think. So back to the nature. It is pretty big, and this is just what we can see. So this is what we've seen with our telescopes, our different types of telescopes. However, the universe is a lot bigger. So it is predicted to be bigger. It has energy that we don't know where it comes from. It has something called dark matter. So there is regular matter, and then there's dark matter. We don't know what dark matter is. It's just we put cool names to things we don't know about. So the universe is still a pretty unknown place. Okay, so we don't know much about it as you might think we do. But every day we know a little bit more, and hopefully our ignorance of the universe becomes less. But remember, you are a part of it, and as complex as this might seem to be so big, you carry one of the most complex things inside of you. Your brain. One of the most complex things in the universe is your brain. So think about that. You're a part of nature, nature is in you. Okay, but let's talk now a little bit about the history of the universe. So, the universe is roughly 14 billion years old. And how did it start? Well, there was this priest called Lemaitre, and he came up with the solution to one of Einstein's equations, so of his theory of general relativity, and it turned out that the universe should have come from a single piece of space that had all the energy in it of the universe in a single little space, a point. We call that the primordial matter, but nobody really knows anything about that. All just that the universe apparently came from a single point. And so how did we go from an infinitely small point, and what I mean by infinitely small is 0.0000 infinitely times, infinite times. And then, so in that little space, boom, all of a sudden there was a huge explosion. And this huge explosion created particles. And these particles carried mass with them. And some really strange physics went on. Okay, all of a sudden the space where these particles were started to expand. And then expanded, and then these particles they had more space to move around. And so there are these forces in nature that started to act upon these particles. Okay, and one of those forces is called gravity. And what gravity did is that after these particles cooled down, so roughly 400,000 years after when the universe was born, then they started to cool down, and they made clumps of matter, and these clumps of matter became eventually galaxies. Okay, but before that, before matter started to clump into galaxies, there's something called the dark ages. Okay, so the first stars started to appear about 400 million years after we had this inflation period. But once the first star was born, that means there was light again in the universe. And the first star is also one closer step to what would become life later on. And why is that? Well, life is made of some molecules, and these molecules are made of atoms. And the different types of atoms that we have in our universe are because of stars. Okay, so stars, they're formed by protons becoming hydrogen. Okay, by a process called fusion. And once this happens, you get more hydrogen and more hydrogen, and eventually you start building up to some atoms, and explosions occur. And after these explosions occur, more atoms are made, and these are different atoms. So the stars are just like the first step of a huge process, and we've made up to the whole periodic table is made up of elements from stars, except for the really last discovered ones. Those are made in particle accelerators, but they kind of simulate what happens in suns too. So not to the same extent, okay, but they kind of simulate it, and thus they can create other atoms, and they can populate the periodic table a lot more. So you see, I'm talking about chemistry here. So physics is related to chemistry, and well, by the looks of it, since stars made the elements that made life, then well, to some extent you could even say it's related to biology. But there is I would say it's been really hard to do quantum mechanics on the scale needed for something like life. So we're still barely starting on that. Okay, and quantum mechanics would be it is a branch of physics that tries to understand what happens on an atomic level. Okay, electrons, atoms, protons, neutrons, what happens with these things? That quantum mechanics tries to explain that. And really funny things happen at that level. Things that contradict your common sense completely. Okay. But that is something that only if you're a physicist you'll really study in detail. But it's a really cool subject though. So after the first stars were born, galaxies were formed, and clusters of galaxies and superclusters, and all the way we have to somewhere around where we are. Now, where we are, the universe is pretty big. It has inflated because apparently the universe is still inflating. Okay, so, and how do we know all this? Well, telescopes have let us been able to measure these things. Telescopes. Okay, and somewhere where I believe the universe is really young. Okay, we still have a lot more to go in this universe. There are many events that will happen to our solar system that are yet to come, and for billions of years. So that's a little bit about the history of the universe. It's hard to describe all of that. But you can get a feel for that a lot has happened for 14 billion years. And okay, so we talked about where we came from. How about where we are? Okay, so we are in a galaxy called the Milky Way, in one of the outer arms. And we're actually in a pretty safe place in our galaxy. Okay, but this is not the picture of our galaxy. This is a picture of a really similar galaxy, but the location is pretty accurate. And then we are in this planet called Earth, the only one we have for now, and we're not doing a good job taking care of it. But young generations will surely join the fight to take care of it. But all that we know, we've known from here. And okay, so where we are, where we came from, but exactly what makes us? Well, we're made of atoms. And atoms are made of even smaller particles. So on one side we have a nucleus with some electrons swinging around it. That's an atom. And on the other side we have what could be a proton. And these UUDs are quarks. Quarks make up protons. Okay, so, but just in case you're wondering, only protons and neutrons are made of quarks. Electrons are made of electrons. We don't know anything that makes up electrons, like protons and neutrons are. But quarks, they're the smallest things we can get to inside a proton. And this is from a branch we call particle physics. Simple name. And well, you might think that there's only those particles, but it turns out there's a whole zoo of particles. So we have a bunch of quarks. We have different types of electrons. You could say that. So there's an electron is something called a lepton. And there are several types of leptons, and they're really interesting objects. There's also what we call the force carriers, or the particles that carry force. But this is this has only been proven to be true for electromagnetic force. So the electromagnetic force can be divided into the weak nuclear force and the strong force. And these are the ones that have these forces. And well, magnetism and what we say electromagnetism, that is related to the photon. Okay, and the what you see as the gluon, that is related to the quarks. The Z and W bosons, those are related to, I guess you could say, electrons and radioactive decay. They are very important in radioactive decay. And then the Higgs boson, which you may have heard in the news. But the Higgs boson is the particle that I would say puts mass on things. Okay, it is a particle that decides, okay, you're supposed to have this much mass, because these particles, except for one, have mass. Okay, so the Higgs does that, and it's a really, really complicated process. I don't understand it too well myself, but you can learn that. Okay, the Higgs is a particle that makes other particles have mass. You can think about it that way. Okay, and see there, I just talked about a few, and now there's twice as much. What does it mean that there's twice as much particles as before? Well, it's their antimatter generation or type. So every particle has an antiparticle, and that's what we have there. So lots of particles. And okay, so we study a lot apparently. I mean, the nature is a pretty big place. I mean, nature, yeah, that's a lot of things. So, and we obviously don't sit down on in a chair and just write down and see how we can figure things out. We have to do instruments. We have to make machines in order to probe the deepest parts of nature, or to make use of the laws of nature. Okay, so what do physicists do? Well, the first picture is the one of ITER. ITER is a reactor being built in France that is supposed to be the first reactor to sustain fusion for, I believe, a couple of seconds. Yes, as much as a couple of seconds doesn't seem like a long time, it is a very long time in physics and in experiments. Okay, so yeah, it's actually a big deal if that thing can sustain fusion for even seconds. And after that, there comes a commercial reactor. But that's what physicists are working on the forefront of energy. And when it comes to telescopes, there is a new telescope that will kind of replace the Hubble Space Telescope. Well, not exactly, but it's the best one we're going to have after the Hubble Space Telescope, which is the James Webb Space Telescope. And that's going to even help us probe other planets and other solar systems better. It has a better mirror and everything. Then there is CERN. CERN is this huge particle accelerator in Switzerland, and that is the place where we probe matter to its most smallest components. Okay, those particles that you saw before, we look at them at CERN. Okay, and how is it that we treat that thing as a microscope? Well, what it does is that it smashes things and it sees what comes out. Okay, so yeah, if there's a funny joke that between physicists that if you want to know what a chicken is made of, just smash it up in the particle accelerator. So that's a pretty rough way to see things, but it is true in particle physics. They smash things and ever harder as they can. Okay, with more energy and more energy. And actually, if it weren't for that machine, we still would be looking for the Higgs boson. Okay, and to know that the Higgs boson is real, that's a pretty big step in physics. Okay, physics doesn't take giant leaps, takes small steps, but those are big steps in reality. Okay, and then the last thing the what is outside the Earth, kind of like flying in space, that is an image I found of a solar sail. Okay, so remember how Alpha Centauri was 4 light years away? Well, it turns out that we can get there in, I believe, was it a little bit over 10 years with a solar sail. Okay, so it's probably going to take a little bit more than 10 years, but ideally a solar sail can speed up the craft up to a quarter of the speed of light, but it's fairly it's kind of a breakthrough of recent years of how that works. I honestly haven't looked at the physics behind it, but if you want to kind of get a clue of what's going on there, it's basically that light is pushing the sail. Okay, so it's going to use the light that comes from the sun, and it's going to push it. That's how it works. But I have high hopes for that, because apparently they're going to try to send a craft in roughly 15 years, so that's not too long away. So 15 years, added another 20 years for information to come back. I don't know. We might see something in another solar system in our lifetime. It's pretty cool. Okay, so that is pretty much all I got to tell you about physics. But I like to read some stuff before I leave. Okay, before our next lesson. So, and this is something I found in a book, in a university physics book. So this is more like when you're going to study engineering or something like that, but I want to read it to you anyways. So if you've ever wondered why the sky is blue, how radio waves can travel through empty space, or how a satellite stays in orbit, you can find the answers by using fundamental physics. You will come to see physics as a towering achievement of the human intellect in its quest to understand our world and ourselves. Wow. And to end my little talk from my little space, I'm going to show you this joke. So we have fields arranged by purity. So we have a sociologist over here. The sociologist is looking somewhere, and the psychologist comes and says, "Oh, you are just applied psychology." But then the biologist comes and says, "Oh, you are just applied biology." But the chemist comes and says to biologist, "Biology is just applied chemistry." And the physicist, of course, which is just applied physics. And the physicist says, "Oh, it's nice to be on top." But physics relies on math. So the mathematician, all the way on the other side, says, "Oh, hey, I didn't see you guys all the way over there." And to a certain extent, it's actually pretty true. I mean, there's more math than what physics can use with. So, but, however, it is important to remember that every branch is important in science. Sociology, psychology, biology, chemistry, physics. Mathematics is a language. It's not a science by itself, but we need that language to express ourselves as universally as possible. And this is where the mocking comes in from physicists. Okay, because chemists are not as good as math as physicists or biologists, or at least that is the thinking. But I hope to see the day where biologists can come up with the mathematical theory just as good as any physical theory. So maybe someday, okay? Or maybe you will do that. Okay, so, okay, yes, I'll see you next time.